Hello everyone. Today we would like to present article named is Digital DAOs. This article is written by Murray Early, Measurement Standard Laboratory of New Zealand. Our presentation is in Electrical Instrument and Measurement 1 in Major Electrical and Electronic Engineering, Faculty of Engineering at เกษตรศาสตร์ University ศรีราชา Campus. My name is ชลวัฒน์ ผสมศาสตร์
My name is ทิติวัฒน์ หัตถกรรม We are spoiled of choice when it comes to making electrical measurement. Digital multimeter (DMM) displaying anything between 3 and 9 digits are readily available. However, despite the accomplishment for their digital device, we must keep in mind that they are complex instruments with imperfection and often subtle but significant faults. Our experience is that many of the high-level DMM submitted to art of calibration have faults or even just odd pattern of behavior of which the owner is unaware. Calibration of art DMM not only provided for tangible measurement but also give us assurance that any such fault will have been identified. Figure 1 shows a simplified model of a DMM in its DC voltage mode. Most imperfections and faults can be classified in terms of the various building blocks or possibly interaction between the blocks. Such a model is therefore vital for understanding the DMM limitation and for determining how a DMM should be calibrated. The essential building blocks are a DC voltage reference. Any shift in this reference will affect all measurements. And a D converter. This is the heart of the DMM and is mainly limited by differential non-linearity, the non-uniformity of successive digital increments. This can be a significant error when the DMM is used to measure small change in voltage and input buffer amplifier. This is a very high impedance amplifier that provides gain of lower range, resulting in greater noise and offset voltage on their length. Scaling by a resistive driver is necessary to bring higher voltage into length of the AD converter at the expense of a lower input impedance. Protection circuitry, which when functioning correctly does not usually detract from the performance.
The typical reading of a DMM as a function of applied voltage is shown in Figure 2 backline. The curve of the line is caused by integral nonlinearity, while the facet for clarity shown only in the middle of the curve is caused by the differential nonlinearity. The red line represents the response of a perfect DMM. A well-designed calibration will make apparent the failure of any of the elements in the block diagram. A calibration process that will achieve this is first characterize the linearity on the most accurate range to quantify the effect of differential nonlinearity. It is impractical to correct for this. but it does become an uncertainty component for other measurements. Measure the gains and offsets on all lanes. It is best to measure the gains separately by measuring the change in voltage that generates a particular change in reading, the blue line of Figure 2. Check additional points on lanes where there are likely to be additional effects, such as integral non-linearity on high voltage ranges, owing to heating of the scaling resistors. While this simplified model gives a handle on identifying the major limitations of DMM, there are many other imperfections: thermoelectric voltage, bias currents, common mode offsets, normal mode offsets, interference from external source, and so on may need to be considered. Using the block diagram approach is a good starting place to account for such effects in these very complex instruments. Thank you.